Good morning, one and all. This is Dr. P Sreenivasulu. Welcome back to the video lecture series. Today, video lecture series PTSP. Today, we are going to discuss about this properties of autocorrelation function in random process. Now, if you consider a signal, a random process signal, now it is a wide sense stationary. Now we can calculate this autocorrelation function. Whenever we calculate mean value of that particular random process, or if we calculate autocorrelation, or if we calculate covariance, and these are independent of time. That is, whenever these are independent of time, then we can say that these are stationary processes, wide sense stationary. Now, here, if you see this Rxx of tau, this Rxx of tau or Rxx of t comma t plus tau. Now, t is a variable. T plus tau is another time instant. It is at one time instant in a random process. This t plus tau is another time instant of in that random process. We are going to see the relation between these two. Correlation means the same random process at a different time instance. We are seeing the similarity between the two time instants. Now, this tau is nothing but difference between these two time intervals, t2 minus t1. Now, if you want to calculate these autocorrelation properties, you see here, first one is the mean square value of x of t. We know what is the mean square value, what is the mean value, expected value of x of t. Mean square means expected value of x square of t. Now, if you calculate mean square value of random process, it is nothing but autocorrelation function at tau is equal to 0. Now, if you observe the proof for this, you consider this formula of Rxx of tau, expected value of x of t into x of t plus tau. It is our general formula for autocorrelation function. Now, in this formula, we substitute tau is equal to 0. We substitute tau is equal to 0. Rxx of 0 is equal to expected value of x of t into x of t plus tau. Tau is equal to 0, another x of t. So, we are going to get expected value of x square of t. So, it is the autocorrelation function at tau is equal to 0 is nothing but mean square value of that corresponding random process. It is the first property. Now, coming for second property, the second property is autocorrelation function is maximum at the origin. If you draw the autocorrelation function with respect to tau, and then if you observe whenever tau is increases on positive side or tau is increases on negative side, the corresponding amplitudes, if you see, that amplitude at tau is equal to 0 is maximum. That meaning of that one is remaining all values of tau, that corresponding amplitude is goes on decreasing towards the time infinity. Now we are going to prove this one. You consider the two time instants. One is a x of t1 in the random process. Another one is x of t2 of another time instant of random process. Now, we are going to be consider this one a positive quantity. Whatever this one, the difference between these two time instants random process. First one is x of t1, whether it is a plus or whether it is a minus. I am squaring this one. I am consider the two time instants random process signal. We can take it as a x of t1 plus x of t2 whole square or x of t1 minus x of t2 whole square, any one. So here for our convenience, we are showing it is plus or minus. It is applicable for plus. It is also applicable for minus whole square greater than or equal to 0. X of t1 plus or minus x of t2 whole square greater than or equal to 0. So it is a positive quantity I have considered. Whenever I am squaring this one, it is positive quantity. Now, if you apply this expectation concept for this, take the expected value and then if you squaring on this one, if you squaring on this one, expected value of x square of t1 and then it is a plus b whole square or a minus b whole square. Next, expected value of x square of t1, x square of t2 plus or minus 2 into x of t1 into t2 is greater or equal to 0. And then you distribute this expected value individual terms. Whenever if you distribute this expected value individual terms, what is the expected value of x square of t1? It is nothing but rxx of tau. Generally, it is a rxx of tau. In that, whenever tau is equal to 0, rxx of 0. Already we have seen the first property. And another, it is another time instant, rxx of 0 plus or minus. It is a expected value of x of t1, t2 is rxx of t1, comma t2. It is nothing but tau. Now, 2 rxx of 0 plus or minus 2 into rxx of tau is greater than or equal to 0. Now, finally, if you take this into mathematical part, finally we will get this rxx of tau is less than or equal to rxx of 0. So, this meaning is the autocorrelation function at tau is equal to 0 is maximum remaining compare with the remaining values of tau. Next one is another property. Now, this rxx of tau is a even function. You know even function. X of t is equal to x of minus t. Then we can say that it is a even or even symmetric. Now, this autocorrelation function is also satisfies even because whatever the reference is at tau is equal to 0, whatever the values we are going to get on positive and whatever the values I'm going to get on negative, if you fold this with respect to vertical axis about the origin, the positive values of amplitudes and negative values of amplitudes are going to be overlap. Then we can say we can say same. We can say it is satisfies even condition. Now it is going to be right in mathematical form. Now, that mathematical form, again, we are going to consider that formula Rxx of tau. So, Rxx of tau is equal to expected value of x of t into x of t plus tau. Now, in this tau, I am replacing tau with minus tau. So, Rxx of minus tau, expected value of x of t, there is no any change because there is no tau. And wherever you have a tau, the tau is replaced with minus tau. And after replacing tau is with minus tau, whatever the t minus tau, the t minus tau is going to be replaced with some other variable that is a u. Now, if you see, now t is equal to u plus tau, it is a one signal. Another one is instead of t minus tau, you can substitute it as u. It is another signal. So x of u plus tau into x of u. Again, if you see this x of u plus tau into x of u, whatever it is, whether it is a t or u or k, it is a variable. Tau is a constant. So it's nothing but rxx of tau. Okay. So instead of t, now we have a u, some other variable. But finally, it is a autocorrelation function between them. So rxx of minus tau is equal to rxx of tau. So it satisfies the even symmetry. Now next you see another property. If a random process x of t has non-zero mean value, that means expected value of x of t is not equal to 0 and ergodic with the no periodic components, then so that ergodic concepts we are assuming like a periodic concept because time average function we are calculating time autocorrelation function, time cross correlation function. So what does it mean? Whenever it is a periodicity, then only we can apply that concept. Now, limit made of tau tends to infinity, Rxx of tau is equal to mean value squaring of mean value. Now, if you see this formula, Rxx of tau, as usual, expected value of x of t into x of t plus tau. It is nothing but it is a one time instant. It is another time instant. Then you take limit tau tends to infinity on both sides. Now limit tau tends to infinity, if you take this Rxx of tau is equal to expected value of x of t1 into whenever these two are independent. Whenever these two, the random concepts are independent. We can apply this concept is a, you see, since the process has no periodic components, whenever there is no periodicity, from tau tends to infinity, the random variable becomes a independent. Whenever it is a independent, we can write separately. Now we know expected value of x of t1 or expected value of x of t2 is nothing but mean value. So it is. So whenever there is no periodic components, it is a independent, then it is a x square. Now next one is, if x of t is a period, then autocorrelation function also we need to prove. Now, what is the autocorrelation function condition? Again, like a random process, any signal, what is the condition for periodicity? X of t is equal to x of t plus or minus some fundamental time period t naught. So here the random process x of t is equal to x of t plus or minus t naught, whether it is a delayed signal or whether it is a advanced signal. X of t is equal to x of t plus or minus t naught, advanced or delayed signal. Now, similar fashion, instead of t, if you write t plus tau, original signal is now, it is another time instant, t plus tau plus or minus t naught. It is the condition for periodic in random process or whatever the condition for any signal periodic condition, that is also we are going to be apply for the random process. Now, if you write autocorrelation function formula, Rxx of tau is equal to expected value of x of t into x of t plus tau. Now, Rxx of this tau, we are applying this periodicity concept, tau plus or minus, whether it is a plus t naught or whether it is a minus t naught. Wherever we have a tau is replaced with tau plus or minus t naught. Now, already we have seen what is the condition. Expected value x of t plus tau is equal to x of t plus tau plus or minus t naught. So, because of it is a periodicity. Then, Rxx of tau plus or minus t naught is equal to Rxx of tau. So that is the difference between there is no periodicity and there is a periodicity. There is no periodicity, it is independent component. Okay. Now next one is, if x of t is a ergodic, has zero mean and no periodic component, then no mean is a zero value. So already we have seen that formula. This limit tau tends to infinity Rxx of tau, it is a mean value. So whenever mean is zero, so finally that corresponding autocorrelation function is zero. So it is about autocorrelation functions. I am going to stop this class. In the next class, we will see cross correlation properties of random process.